Hello, everybody. Welcome, Santa Cruz, to our first virtual Astronomy on Tap. I have to admit, I'm a little nervous about this. This is exciting and it's new, and I'm very interested in hearing how this works out. And usually when we do the live events, if you've ever been there, this is usually when in my role as MC of the event. By the way, if you don't know, I'm Alexa Viome. I am now a former graduate student from UCSC's Astronomy and Astrophysics department. I graduated. And so we usually put on a live event at Santa Cruz Mountain Brewing. But obviously world events have gotten in the way, but we're happy to bring the virtual event. And as I was saying, this is usually at the point where I try to pump up the audience and I go, who's been to an Astronomy on Tap before? And people go, ah! And I go, who's never been? This is the first time. And people go, ah! But I can't do this time. But I would like assurance that we have an audience. So if you are listening in on the YouTube live stream, please say hi. Tell us, say hi. Say how you heard about us. Say if it's your first time for an Astronomy on Tap event. The YouTube live chat is also where you can post any question you're interested in at any time during the talk. This is a little bit new, so let me explain what we're going to be doing this event. So we have two amazing speakers tonight. The first speaker is doctoral candidate in the Astronomy and Astrophysics department, Maggie Thompson. She's wonderful. And our second speaker is Dr. Myriam Telus, an associate professor in the Earth and Planetary Science department, who is an advisor on Maggie's thesis. And if you saw our flyers, you know that they use meteorites to learn about the solar system and more. So I'm excited to hear about that. For those who have been to an Astronomy on Tap event, we will not be doing a quiz today. Unfortunately, we just decided for our first run to just simplify things. So it'll be the two talks. After each talk, I will have the collection of any questions that anybody asked, either through the YouTube live link or through Instagram or through Twitter. And I will be asking the questions to the speakers on your behalf. So I'm very excited. But first, before we get into the speakers, I would like to welcome Ashley, the events coordinator from Santa Cruz Mountain Brewing, who we've collaborated with for our live events, and we're collaborating with for our virtual events. Hey, Ashley.
Hey, Alexa, how are you?
I'm doing well. How are you?
Good. I wanted to cheer and applaud. Congratulations. I'm so happy that you graduated.
Oh, thank you. Thank you so much. Do you want to tell us a little bit about what's going on with Santa Cruz Mountain Brewing during this time and what we can expect in the near future?
Well, who really knows about the near future, but what we're doing this week and what we've been able to do for the past couple of weeks that's really exciting is get to use the beer garden, get to use the new completely renovated space. So the tap room is open for service from 12 to 5 Thursday through Sunday, and then we're doing until 8 Friday, Saturday. So that's really exciting to be able to go out and be outside and enjoy hanging out with your friends. It's been way too long.
Yeah, that's amazing. I can't wait to pop by. And I like the amber ale there. That's my fave. So I'm excited about that. So I think now we're going to introduce our first speaker, Maggie. Talk to you later, Ashley. Maggie, come online. It's Maggie!
Hi, everyone.
Space! Maggie, have you seen those pictures of corgis in Hubble Space Telescope photos?
No, but I
haven't?
Me too. Yeah.
You have to Google that immediately. It's awesome.
That's amazing. That's amazing. Corgis are wonderful.
Yeah. And speaking of dogs, do you have a little friend with you today?
I do. Let me bring her over. Here, she's coming right over. I have a little Shih Tzu named Rocket. She's getting passed off to me by my nice boyfriend, Jeremy. Here she is.
Oh, it's Rocket.
Say hi. She's been struggling through quarantine, not getting to hang out with her dog friends, but we're doing
Oh,
okay.
Rocket's just like the rest of us.
Truly.
One of the things that I really miss about the live events is I always love seeing people's dogs during the event. So I encourage anybody who's listening to send us pictures either through Twitter or Instagram of your dogs, your cats, your beers you're drinking, anything. Like, I am desperate for human interaction, so
Yes.
bring them our way.
Rocket loves Santa Cruz Mountain Brewery. We went there for Halloween and she won, I can't remember exactly what it was, but it was funniest Halloween costume. And I think to this day, that's her proudest moment.
What was her Halloween costume?
I was a meteorite, actually technically meteor, which I'll talk about in this talk tonight. And she was a dinosaur.
Ooh, I love it. It's kind of cruel to Rocket though, don't you think?
I know it was a little bit.
So Maggie, how have you been holding up through the pandemic and shelter in place?
It's been okay. It's definitely a little weird. As you all might assume, Dr. Tellus and I both work in a lab, which obviously with COVID, we were not able to do that for the last few months. So that's been hard, but we are looking forward to getting back into things now that things are starting to open up.
That's great. Have you picked up any hobbies or activities?
I have actually just started knitting. That's been a big hobby of mine throughout quarantine. And so I'm actually wearing my very first knitted sweater. So I have to shout out to a few fellow grad students, Diana, Emily, and Camille, who really taught me everything that I know and have made this whole thing possible. So that's been really fun.
That looks very cozy. I feel like you should be on the Irish coast somewhere.
Yeah, I'm a little sad that I finished this right before the summer, but that's okay. I know it'll serve me well for a while.
Well, you have something to look forward to in the winter.
Exactly.
Well, Maggie, I am going to hand it off to you. And just a reminder for everybody, you can post any questions you have for Maggie anytime. No question is too small, no question is too big. And I will ask the questions, have a little chat with Maggie after your talk. So Maggie, it's all you right now.
Thank you so much, Alexa. Okay, great. I'm going to share my screen with you all. Okay, great. Well, welcome everyone. Thank you so much for joining us for our first virtual Santa Cruz Astronomy on Tap. This is really exciting. As Alexa said, my name is Maggie Thompson. I am a third-year graduate student at UC Santa Cruz, working with Dr. Tellus, who we'll hear from next. And this evening, I am really excited to get to talk to you all about meteorites. Over the next few minutes, we're going to together investigate not only what meteorites are, but also how they can serve as windows into our solar system's history and potentially beyond that to the history of planetary systems that orbit stars other than our sun. Oops. Hold on, there we go. Great. Okay, so before we get started, here's a brief roadmap of where we're going for the next few minutes. We're going to start by talking about what meteorites are, where they come from in our solar system, and the different types of meteorites that we have in our collections. Then we're going to investigate how meteorites can not only tell us the age of our solar system, but also many different things about the history of our solar system and even our own home planet Earth. Then finally, we're going to conclude by discussing how meteorites can also inform the atmospheres of planets that orbit stars other than our sun. These are exoplanets. And like Alexa said, I just want to remind you all here, please feel free to ask questions throughout my talk, particularly through the chat window on YouTube Live, and you can also tweet or message us on Instagram as well with these handles. So let's start with, what are meteorites? Meteorites are rocks from space, really any extraterrestrial rock that lands on Earth. Most meteorites come from the asteroid belt. This is a collection of asteroids, which are rocky, airless bodies that are remnants left over from the early history of our solar system. You can almost think of this asteroid belt as almost like a space rubble pile. And this is located between the orbits of Mars and Jupiter. We also have meteorites in our collections that come from Moon and Mars as well, but most of them come from the asteroid belt. Meteorites are really awesome because they give us a record of the building block materials that went into forming planets, and also give us clues into processes that took place early in our solar system's history. I actually have a meteorite with me now, which I realize with my background might be hard, but I'm going to try to bring it close to the camera. So this is a meteorite that fell in 1947 in Russia. This is just a little piece from it. Now, when people think meteorites, you all might have heard a number of different terms. So I wanted to spend a few minutes just talking about some terminology here. So a meteor is a body of matter that is from space that enters Earth's atmosphere and appears as a streak of light. This is really when we talk about shooting stars, that's what we're talking about here. And once it lands on Earth, then we call it a meteorite. Some other terms you might have heard before are fireballs. This is just a term to describe a really bright meteor. You may also have heard the term bolide. This is another term to describe a special type of fireball, which at the end, when it's nearing its collision with the surface of the Earth, it explodes. And this is due to the fact that it's entering thicker parts of Earth's atmosphere. And then many of you may have looked up at the night sky during a period when there's a meteor shower. And this happens when Earth is passing through some leftover debris from a comet that's on its orbit and is getting closer to the sun. And so because some of these comets are on these highly elliptical orbits, you see them around the same time every year. So where do we find meteorites? This map here shows 500 years of witnessed meteorite falls. This is human records of seeing a meteor fall from the sky and then land on Earth and become a meteorite. Now, you'll notice this happens kind of all over the globe. And of course, meteors are probably flying and landing ultimately in the oceans as well, but humans aren't there to record them. In fact, actually, most of the meteorites in our collections were not witnessed to fall. They actually were just found many years after they fell to Earth. Around 65% of meteorites are actually found in Antarctica, and another 18% are found in the Sahara Desert. And these are both really good places to look for meteorites because it's relatively dry and flat, and there's not a bunch of other rocks around to be confused with meteorites. So now, what types of meteorites do we have in our collections? The first are primitive meteorites. These are known as chondrites. Chondrites preserve the early composition of the solar system. They're really special in the fact that they only experienced mild heating. They were never hot enough to actually melt. And so they really give us this record of what was going on with the first bodies that formed in our solar system. Chondrites are stony mixtures, kind of similar to sedimentary rocks here on Earth. And they're these collections of dust grains and particles that formed under various conditions early in the solar system's history. Now, the second type of meteorites that we have are called achondrites. These are the melted meteorites, and these form throughout planetary accretion, or this is essentially, you can think of that as just the growth of planetary bodies, and not just planets, but also even smaller planets. Normally, we call these the planetesimals, or also planet parent bodies for these meteorites. They provide records of differentiation. This is a process by which heavier material sinks to the center. And as part of that is also core formation. You can think of this as the same way this happens on smaller bodies, just like it happens on Earth, where we have their core and our mantle. And achondrites include both stony rocks and also iron meteorites, and also some that are a combination of these two. And if we look at one of these really up close, some of these iron meteorites exhibit these really cool patterns. These are called Widmanstatten patterns. And this is really just iron nickel crystals that make this beautiful pattern when you dissolve these iron meteorites in some acids. You can see this cool pattern. So now let's get into our second topic. What do meteorites tell us about solar system history? So to answer this question, let's do a quick review on solar system formation. So it all began about 4.6 billion years ago in a molecular cloud. This is a cloud of dense gas and dust. This cloud starts collapsing on itself. And this may have been due to a shock wave that was caused by a nearby star that explodes. And ultimately, it causes this cloud to compress, and it ultimately results in a flat spinning disk of gas and dust. Once enough material collects at the disk center, what ends up happening is you can get nuclear fusion. When things are hot and dense enough, hydrogen atoms are able to convert into helium, and essentially our sun is born when this process takes place. Now, most material, and when I say most, I mean 99.8% of this material goes into forming our sun. The very little amount of material that's left over starts to clump together and form planetesimals. These are small planetary bodies that will eventually form planets. So these planetesimals will end up colliding together to not only form planets and moons, and also dwarf planets like Pluto. And ultimately, the asteroids and comets that are in our solar system provide remnants of these planetesimal material that form the planets. So ultimately, that led to where we are today. So how do meteorites help us put together our understanding of how the solar system formed? Here, I'm showing a primitive meteorite, an example of a chondrite like we just talked about. This one is called NWA 2086, really exciting name. This was found in Northwest Africa in 2003. And you'll notice there's this white inclusion in the center here. This is called a calcium aluminum inclusion, or a CAI. These inclusions are found often in primitive meteorites, and they're not only the oldest components in chondrites, but they're also the oldest objects to form in our solar system that we know of. They can range in size from millimeter to centimeter size objects, and they can have various textures as well. And the really exciting thing about CAIs is that we can date them using this technique called radiometric age dating. And this technique uses radioactive decay. And this is when an unstable atom emits particles to become stable over time. And since each radioactive atom or unstable atom decays at a certain rate, you can use this as a clock to ultimately tell you how much time has passed since the object that contains these atoms formed. And so thankfully, we can use this technique to determine the age of CAIs. We find that the oldest ones are 4.567 billion years old. And since these are the oldest objects that we know of in our solar system, they are used to tell us how old the solar system is. Now, not only can meteorites tell us the age of our solar system, they can also tell us about its early history. So as we discussed during our rapid tour of the solar system, once the sun is born, we have this leftover material of dust and gas in the disk, and ultimately these dust grains end up collecting together to form planetesimals. Planetesimals are the building blocks of planets. They're these small planetary-sized bodies. They can range anywhere from a few meters all the way up to several hundred kilometers in size. And then these planetesimals will end up colliding and collecting together to form planets and other larger bodies like moons and dwarf planets. The asteroids and comets that we have in our solar system today are remnants of these planetesimals. And since most of the meteorites in our collection come from the asteroid belt, they give us direct information that we can study in the lab here on Earth to understand this population of planetesimals and ultimately how our planets formed. So these meteorites are really important because they give us a record of the different stages throughout our solar system's formation. And since we can also date meteorites with radioactive decay, they can help us piece together this timeline of how we started with this disk of just dust and gas to ultimately end up to where we are today with the planets in our solar system. And not only can meteorites tell us about the early history of our solar system, they can also tell us about the building blocks for our own planet Earth. And so one of the ways that meteorites can give us clues into the building blocks for Earth is by looking at isotopes. Isotopes are atoms of the same element that have different numbers of neutrons. So I'm just showing here a few examples of some of oxygen's isotopes. And for many isotope systems, we find that the composition of the Earth is very similar to certain groups of primitive meteorites, or these chondrites. And so I'm showing that on this plot here on the right. So what you're seeing is the oxygen isotope ratio on the y-axis, and then on the x-axis, we're looking at the chromium isotope ratio. And you can see where Earth plots in this little green square here. And then all those black circles represent different types of primitive meteorites, different types of chondrites. And what we end up finding is that we can combine different types of these primitive meteorites to ultimately reproduce what we get for Earth. So ultimately, meteorites preserve a record of the planetary building block materials that formed our planet Earth. Now let's move on to our last topic for today. What can meteorites tell us about exoplanets? First, I think we should do a brief little review on what exoplanets are. So an exoplanet is a planet that orbits a star that's different than our sun. And this plot here is showing planet mass in units of Earth masses as a function of planet's distance from its star in astronomical units, AU, that's the distance from Earth to the sun. And all those blue points there are showing you all the different exoplanets that we've discovered to date. And then the stars are just showing you where Earth, Venus, and Mercury plot on there for scale. But remember, these planets orbit stars outside of other than our sun. They are around other stellar systems. And what's really amazing is to date, we've discovered over 4,000 exoplanets. So it's a really exciting field in astronomy right now. And since we can't visit these planets anytime soon, they're much too far away, in addition to just understanding their basic properties like mass, size, and distance from the star, the only way we are really going to be able to understand what these planets are like is through studying their atmospheres. And the atmosphere is this envelope of gas surrounding a planet. Now let's just briefly talk about the two main mechanisms for planets to obtain an atmosphere. The first method are what referred to as primary atmospheres, and these form by capturing hydrogen-rich gas in the disk. Remember, we were thinking about how planets end up forming, and you have this disk of gas and dust. So really, if these planets get big enough, they can just hold on to some of the gas, and that forms their atmosphere. This is the main mechanism by which the gas giant planets like Jupiter and Saturn obtain their atmospheres. Then the second technique is referred to as secondary atmospheres. These form instead through outgassing, essentially release of gaseous species as a result of heating during the planet formation process. And then also that can happen later on through tectonic processes like volcanism like we have on Earth today. And this technique is believed to be the main mechanism for low mass rocky planets like Earth to obtain an atmosphere. And I'm really interested in these for my own research. So we're going to kind of focus on these types of atmospheres for the next few slides. So ultimately, what can meteorites, though, tell us about the atmospheres of exoplanets? As we just discussed earlier in the second part of the talk, the inner planets in our solar system formed out of material analogous to meteorites. Remember, these meteorites preserve a record of the planetesimals that ultimately formed our planet Earth. Rocky planet atmospheres, like we just discussed, likely are going to form their atmospheres through outgassing as they're forming. So therefore, if we measure the outgassing composition from meteorites, this can help inform the sort of atmospheric composition that you would get from rocky planets forming through outgassing. And so this is just an example of the type of research that we're currently conducting at UCSC. Here's a picture of our meteorite heating laboratory. I'm showing a furnace in the major big box here in the middle, which is connected to an instrument called a residual gas analyzer. This is a type of mass spectrometer, which is an instrument that essentially measures the abundances of gas species that get heated from that are released from your meteorite sample and then flow into your system here. And so Dr. Tellus and I use this instrument to ultimately inform what sorts of gas species are released from meteorite samples as a function of the temperature to which you're heating these meteorite samples to. This laboratory is located really close to natural bridges for those Santa Cruz locals or people that have visited Santa Cruz in one of the Santa Cruz research facilities. And then on the right here, I'm just showing a sample of our results. So this is showing for a set of different chondrites that we've heated. This is plotting on the y-axis abundance, and then on the x-axis temperature. And then all these different curves are showing you the abundance of these different gas species that are released upon heating these meteorite samples. So things like water or carbon monoxide or carbon dioxide. And Dr. Tellus and I are currently conducting this research in order to understand when gas species are released from different meteorite samples, at what temperatures does this happen, to ultimately inform the types of early atmospheres you may expect for rocky, low-mass exoplanets. So I have just 4 main take-home points for you all tonight, and I encourage you to all go home and tell all your friends or anyone that wasn't able to join the live stream, tell them all about what you've learned. The first is that meteorites are rocks from space that fall to Earth, and they are really special samples because they provide records of planetary building block materials, these planetesimals. The second is that calcium aluminum inclusions, which are found in these primitive meteorites, those chondrites, they tell us the age of the solar system. They tell us that the solar system is 4.567 billion years old. The third is that meteorites not only tell us the age of the solar system, but they also give us clues into the processes that occur early in the solar system's history. For instance, planetesimals colliding to form into planets. And they also tell us about Earth's own building block materials. And then finally, meteorites can ultimately inform the possible atmospheric compositions that you may expect for rocky exoplanets. And then finally, before I conclude, I would just like to thank my amazing PhD advisor, Dr. Tellus, who has truly helped me in countless ways throughout my graduate career. When I started at UC Santa Cruz, I had never done any laboratory research before, and she has given me so much guidance and support to really make me a laboratory scientist. And so without her, truly none of this would be possible. So thank you all so much for listening, and I will happily take questions.
Oh, great job, Maggie. I'm just trying to recreate the live audience experience for you the best I can.
Thank you. I appreciate it.
So, I mean, just a host prerogative, I'll take the first question, as is the thing in astronomy.
Yeah.
I mean, can you describe a little bit, like, how did you get into this? Like, can you just say, like, how did you even know to want to become a laboratory astrophysicist?
Well, it's actually really funny. So I truly owe so much of this to Dr. Tellus. She and I met, I did a gap year before I became a grad student at UC Santa Cruz. And I did research in Washington, D.C. at an institution called the Carnegie Institution for Science. And at the time, Dr. Tellus was a postdoc there. And so we met, and I remember thinking, she does the coolest research ever. Like, I don't know anything about space rocks, but this sounds awesome. And she basically then coincidentally ended up at Santa Cruz too. And so she and I kind of got talking from the day that I started at UCSC. And I was like, I want to do a project with you and like related to meteorites in any way. And so it's been great. She's had to, teach me all sorts of things. From the first time I crushed up a meteorite, I think I put my face a little bit too close to it. And she was like, you probably don't want to inhale that. So yeah.
That's amazing. Okay, so we've got some audience questions. Thank you, everybody. Keep them coming. So first, why does it seem that so many meteorites land in Russia?
That's a great question. Russia is very big. So my guess is it might just be partially that, but also I think people might think about, there's that famous video that I know I've seen, even if it's just a few clips of I think it really is a bolide, where it's a meteor entering and then it kind of explodes at the end, and a bunch of people recorded it from their cars. And so I think that might have drawn a lot of attention, but my guess is it's just really big. In fact, the most common place, though, to find them is really Antarctica, and people will go out on scientific expeditions and spend a few months looking just out on the Antarctic tundra for meteorites. So that's where we actually find most of them. But I do think in the news you see a lot about them being from Russia.
That's amazing. That kind of leads into the next question. So what exactly are the distinguishing characteristics of chondrites? Could you be able to tell the difference between a meteorite and just a rock with your naked eye? Like, can people go out and look for these things?
Absolutely. Yeah, you definitely can. And even if you just Google, how to identify a meteorite, there's a lot of really good resources online. For chondrites, these primitive ones, oftentimes you really want to be able to slice them down the middle and really look inside, because oftentimes when meteorites fall to Earth, they end up, when they're going through the atmosphere, they end up with like a fusion crust. And that's kind of like what you can sort of see on this one. Like, it just looks kind of shiny. And so if you were to slice this open, it would look different. And so when you look at chondrites, they have these cool things called chondrules, which are these like roundish metal droplets, essentially, that were like melted material. So you can actually kind of detect those as well. So yeah, there's a lot of great laboratory techniques to identify them. But some too, like if you think you found one on a hike, there's certainly techniques that you can do even at home to try to identify them.
Amazing. Maybe we have some treasure hunters in the audience looking for a new hobby.
Exactly.
So can you tell us a little bit more about the samples? Like, how much of a meteorite do you need to heat and get useful information out of? Like, does it matter if you have a little meteorite versus a big meteorite?
That's a great question. So thankfully, because in the experiments that I'm doing, I'm kind of to some extent destroying these samples by heating them up in a furnace. So thankfully, I only need a few milligrams of material in order to conduct these experiments because, we have a decent amount of meteorite material on Earth in our collections in museums, but of course it's really precious material. So we don't want to be destroying a lot of it. So for my experiments, I just need a little bit. And actually for most experiments and different laboratory techniques, you don't need a ton of material. And some techniques are also non-destructive. So that's great as well.
Amazing. So I think one of the great, funny stories in astronomy is for a long time, astronomers thought they really knew how solar systems form. Like they really thought we nailed it and we understood it until we started finding other solar systems around and exoplanets and things like that. And that really tanked our theories of solar system formation. And so do the element compositions of the meteorites, like does that help inform how we understand the formation of solar systems outside of our own?
So that is a great question, and you will hear more about this in Dr. Tellus's talk. So that's a fantastic question. I certainly think to some extent, and my own opinion, and we'll kind of see after Dr. Tellus's talk, but I think to some extent these really do help us because, for all studies of other planetary systems, we don't have the luxury of being able to take a scoop of that planet or that system to really study it in depth in the lab. So for now, for the foreseeable future, meteorites really are going to be our best tool that we can directly study in the lab. But there's a lot of great astronomical, observational techniques too. So we have to be sure that we combine both of them.
Yeah. So I think probably it's most people in the audience have heard of carbon dating. So is this essentially what you're doing and just using chromium and oxygen instead of carbon? And why do we use carbon for Earth things and why do we use chromium and oxygen for space things?
That's a great question. Yeah, it's a very similar process. So when we're looking at these things like radioactive decay, there's a lot of different elements that you can use because for different elements, some of their isotopes end up being unstable. So at least for instance, these calcium aluminum inclusions that I was talking about, oftentimes you use like lead dating. Actually, that's the best technique. But there's other elements too that you can look at as well. For carbon dating, my best estimate, and I'm by no means an Earth scientist, but my guess is that can give you some of the most accurate measurements. And that's the big tricky thing when you're looking at radioactive dating is you have a wide range of elements to choose from. And you not only want to pick the technique that you know exactly the decay timescale really well, but you also want to be sure that there's enough of whatever material that you're going to date. There needs to be enough lead or enough carbon in those rocks to ultimately date them. So I know for Earth, a lot of Earth rocks have a lot of carbon in them. So that's probably the main reason for that. For meteorites, I think potentially that technique could work as well. But for getting absolute ages that go that far back, you need these long-lived systems. And so heavier elements tend to.
So these are the heavier elements than carbon that decay longer.
Right.
Yeah.
Exactly.
And then, so, you talked about these planetesimals and you said planetesimals then become planets. Can you speak a little bit to what happens in between that? How do planetesimals bind and become planets?
Totally. Yeah. It's a really interesting process. I think, a lot of times, even in the schematic that I showed, it almost looks like it's this really violent, period where you have these planetesimals, crashing into each other. But a lot of times, actually, these collisions can just end up where these things end up sticking together. It doesn't necessarily always have to be like these really violent collisions that end up breaking things apart. So it's a combination of, sort of slow, collisions that end up just where the two particles will stick together, and that happens slowly over time. And this is something that meteorites can help tell us, because you have a real mixture in this phase of planet formation. You have some bodies that, you know, got hot enough that they already, even just as like asteroid-sized bodies, started melting. They formed their own little mini cores. And you have others that didn't. And so it's a really varied history, and trying to piece together how all of that happens and when is certainly, you know, tricky, and something that people are still actively working on. And it's not necessarily that like each phase is distinct. You might have these things melting, violent collisions, and then also some, you know, easier, smoother collisions happening at the same time. So there's a lot going on.
So cool. So one last question, and this is my own question. So I'm wondering, have you heard anything about the renewed buzz about Oumuamua, the interstellar object?
If it's potentially related to our own UCSC professor, Doug Lynn, I'm trying to remember, and I should, but you can maybe remind me if I'm forgetting.
Well, I saw a New York Times article that was about a study from actually a previous UCSC professor, Greg Laughlin, now at Yale, who is saying, so for those of you at home who might not be familiar, Oumuamua is the name of this object that was detected about 2 years ago now, and it was very quickly established, based on its trajectory, that it was not an object from within our own solar system, which is the first time, right, that's happened, that we've detected such an object.
Right.
And so there's been this, there's a lot of fantastical ideas of what this could be started coming. It's an alien spaceship or something like that. But what they're saying is, and then a more kind of stayed and established theory was that it's just an interstellar comet. But what this new study by this professor at Yale and this postdoc at University of Chicago, they say, based on their composition analysis, it's likely a frozen block of hydrogen that came from the center of an interstellar dust cloud that like forms stars. Did you hear about that?
No, this is awesome though. I'm gonna go.
I know, it blew my mind.
Well, no, I mean, I think these like Oumuamua has really opened up an entire new possibility that I think people didn't really think too much about. It's likely that we've had these bodies, whether it is this like block of hydrogen or maybe, even rocky bodies that have come from not in our solar system, but have entered our own solar system at some point in time. And it's really interesting because there's been cool studies saying maybe you need these, extra stellar objects to help feed planet formation. I'd be really interested. Yeah. Cause maybe I'm curious if they're saying the hydrogen maybe helps explain the crazy shape that this thing has, because it's odd, elongated shape. That's super cool. I'm gonna look that up.
Yeah, it's amazing. You should look it up. Yeah. Well, Maggie, thank you so much. This has been wonderful. It's your time to relax. Yeah.
Who's out? Thanks, everyone.
See ya. All right. And so before we move on to our next speaker, Dr. Tellus, I'm just going to give a quick plug for the audience. So we at Astronomy on Tap, we want to make sure we're serving and communicating with as a representative cross-section of Santa Cruz as possible. In the YouTube live chat link, there's a link to a demographic survey. You don't have to, but we would love it if anybody who's watching this at home could fill out the survey, tell us who you are, what your interests are, how you heard about us. This helps us make better programs, better events, and so please, just if you get a chance, just fill out that survey, just so we know who we're talking to here and who we might be missing. And with that, it's time to introduce Dr. Tellus. Dr. Tellus, start your video, if you please.
Hello.
Hi, how are you doing?
Good. How are you?
I'm doing pretty good. I'm having fun. Thank you so much for joining us tonight.
Oh, it's a pleasure.
Yeah, before we get into it, I just wanted to chat a little bit, introduce you to the audience. How long have you been at Santa Cruz?
August will be 3 years now.
Wow, that's amazing. And so you're in the Earth and Planetary Science
Yeah.
department, is that right? So do you consider yourself, or does it even matter? Do you consider yourself an astronomer, or do you consider yourself a planetary scientist?
I consider myself a planetary scientist. Yeah, I
Mm.
don't use telescopes, so I,
Ah,
I, I assume astronomers do observations, but my guess is they're probably more broader, they probably do more broader science than that, but that's what I kind of assume
yeah.
the astronomer's job.
Well, that's fun. So has it been hard these last few months? Like, how do you do your research when you can't access your lab for months and months?
Yeah, you don't do well. I have a lot of data. The nice thing about having a lab is that first of all, I really enjoy working in the lab. So I enjoy collecting data and seeing new samples and learning about new samples. Um, but that means I have a lot of data all the time. So this time has been good for me and my students to work on writing up what we've already done and
Yeah,
sifting through our piles and piles of data. So that's what I'm
yeah.
trying to do with this extra time.
I can see how that's nice. Is there any end in sight? Like, are you going to be able to get back into your lab at any point? Do you know?
Yes, actually, our postdoc, she's sort of our guinea pig. She's the one she has really time critical work to do in the lab. So I've given her permission to go in and use the lab on her own. So hopefully no need to worry about, COVID because she's the only person in the lab there.
Yeah.
So she's sort of dealing with all the new rules and everything with going to campus.
Mm-hmm. Yeah, it's a very weird time, right?
It's like Twilight Zone. It's like
I,
completely.
yeah. Well, I will let you take over now.
Okay.
I'm looking forward to hearing your talk and talking to you at the end. All right.
Okay. Thank
All
you.
right. Thank you.
So I'm sharing my screen now. Hope everyone can see. Hello, everyone. I'm so excited to be here. And I'm excited that I get this opportunity to help kick off this virtual edition of Astronomy on Tap. So you just heard Maggie talk about meteorites. She mentioned how there are pieces of planetary building blocks called planetesimals that went into forming larger bodies. And she discussed how meteorites can potentially be used to study the composition of atmospheres of exoplanets. For my portion of this presentation, I want to delve into our assumption that meteorites can be used as analogs for planetesimals in other solar systems. So for this talk, I will discuss what we know about planetesimals here in our solar system, what we know about planetesimals there in other solar systems, and see whether meteorites can be used as an analog to study planetesimals everywhere. Planetesimals are small planetary bodies that form almost immediately after the solar system's formation. They form through collisions and sticking of dust particles and pebbles. Their sizes can range from a few meters to hundreds of kilometers, as Maggie said. For comparison, the largest types of planetesimals are just a small fraction of the size of the moon. With time, most of the planetesimals were gobbled up by the sun, or they went into forming larger bodies through collisions between planetesimals and protoplanets. Ultimately, this whole process resulted in the solar system structure as it is today. Asteroids and comets are remnants of the population of planetesimals that went into forming our solar system. Most meteorites come from asteroids. Asteroids are remnants of rocky planetesimals that formed in the inner solar system. They occur in a wide variety of compositions and shapes. So here you can see Eros. Eros is a 16-kilometer diameter asteroid. It has a composition similar to the composition of the most common meteorites found on Earth. This asteroid has a very irregular shape, as you can see, and it's covered in craters. Itokawa is a small asteroid called a rubble pile asteroid. It's a mixture of really fine-grained material and boulders. The Japanese Space Agency, JAXA, collected and returned samples from this asteroid in 2010. It has a composition similar to Eros and to the most common meteorites on Earth. Here are asteroids that are worth mentioning because there are current missions to these objects. Ryugu is a 1-kilometer diameter asteroid. JAXA recently collected a sample from this asteroid, and it should be returned later this year. It's expected to be similar to a carbon-rich type of meteorite. Bennu is similar to Ryugu. It's much smaller in size. NASA currently has a spacecraft orbiting this asteroid, and it's expected to return samples from this asteroid in the next couple years. It's also expected to be a carbon-rich, similar to carbon-rich meteorites. It's not clear exactly what these planetesimals originally looked like, because the asteroids that we have now, they've clearly been battered and reconfigured by billions of years of impacts and collisions between asteroids. There are other types of planetesimals represented by comets and possibly some Kuiper Belt objects, but we do not have this material in our meteorite collections as far as we know. Overall, meteorites tell us that there were more or less 3 types of planetesimals: differentiated ones that have a metal core and a silicate mantle. So these planetesimals were heated enough to melt rocks and separate the material by density. Then there were metamorphosed planetesimals. These planetesimals experience heating, but not enough to cause the rocks to melt and differentiate like the differentiated ones. And then there were the unaltered or primitive planetesimals. These do not show evidence for significant heating. And before I move on, let me show you one of the meteorites Maggie was talking about. So this is a chondrite, hard to see, but I've sliced it and polished it. And you can see the inside looks different from the outside. Okay, so that's a brief summary about what we know about planetesimals in the early solar system based on the meteorite record. So the question I want to address today is whether meteorites and the planetesimals they represent can be used as analogs for studying planetesimals and planets around other stars. As Maggie mentioned, we have been approaching this question by saying that we're not sure what planetesimals are like around other stars, but meteorites are the only material available to directly test how the composition of the initial building blocks influence the composition of exoplanet atmospheres. But for this discussion, I wanted to take advantage of this opportunity to basically see if there's actual evidence to support that planetesimals here are similar to those that formed around other stars. To address this question, we must look to the composition of stars, because that is the most direct way to try to study the composition of the planetesimals that formed around them. So stars occur in a wide variety and have life cycles that depend on their initial mass. Stars are classified by their luminosity and surface temperature, as shown by this diagram here. Most of the elements heavier than hydrogen and helium were produced inside stars and spread across interstellar space during supernova events. We'll talk about white dwarfs really briefly, so I want to mention them here as well. White dwarfs are the final stage of stellar evolution for low mass and intermediate mass stars like our sun. These stars are very hot, but they have low luminosities due to their small size. So they're dim, they're not very bright. The composition of a star can be measured spectroscopically by analyzing absorption lines from a star's photosphere. So here's a portion of a portion of the solar spectrum. So this is the light that comes off of the sun. And the absorption lines are these dark bands. The strongest absorption lines you see here correspond to iron, nickel, and copper. As I mentioned earlier, the most direct way to study the composition of planetesimals around other stars and compare them to the meteorites and the planetesimals that formed in our solar system is to look at the composition of the host star. So let's see why that's the case. Here is a plot showing the abundance of elements in the sun on the y-axis and the abundance of elements in the most primitive meteorites on the x-axis. The diagonal line across this plot is a one-to-one line, and that the points that fall on this line have similar compositions. So this plot is showing a striking similarity between the composition of the sun and the composition of chondrites. There are only a few exceptions here. That's nitrogen, carbon, and oxygen. These are more abundant in the sun than in chondrites. This is because these elements strongly prefer to be in the gas phase, so they do not want to form rocks. And then lithium is more abundant in chondrites because this element is destroyed by nuclear reactions within the sun. The close agreement between the composition of the sun and the composition of chondrites indicates that the disk, the protoplanetary disk, the disk where planetesimals and planets formed, was very similar in composition to the sun. So to summarize, since primitive meteorites and the sun share a similar composition, this means that planetesimals formed from a disk similar in composition to the sun. Therefore, we can use the composition of the host star to constrain the composition of extrasolar planetesimals that formed around that star. Okay, don't forget to ask questions. I meant to say that earlier. Okay. Here is the same plot from before, but this time I have highlighted the elements that can be measured in other stars besides the sun. As you can see, astronomers can measure an impressive number of elements in other stars though the precision is generally not as good as what we can do for the sun. Okay, so now I will discuss what we know about the composition of sun-like stars, and then I'll go into what we know about the composition of a more general population of stars, and then I'll briefly discuss white dwarfs and what we know about planetesimals from white dwarf stars. So first, we want to look at sun-like stars, also referred to as solar twins. These stars are categorized based on a number of parameters, including the surface temperature and the age of the star. Looking to solar twins is an intuitive first approach if you want to know whether meteorites can be used as an analog to planetesimals elsewhere. It makes sense to look for stars that are similar to the sun. If the composition of the star is similar to the sun, then the composition of the planetesimals could be similar to what meteorites record. Here is a plot showing the abundance of different elements in solar twins relative to the abundance of iron. So that's what this is showing. These values are for the average these values are an average of 11 solar twins within the solar neighborhood. So on this plot, 0 means that the solar twin and the sun have identical abundances of a specific element. The x-axis shows the condensation temperature for these different elements. The condensation temperature is the temperature at which these elements change from a vapor phase to a liquid phase or solid phase. Overall, these studies like this one, indicate that the composition of solar twins and the sun are very similar. That's because the range in these abundances are very limited compared to when you compare it to a more general population of stars. So at least for sun-like stars, meteorites could be used as an analog for the planetesimals that formed around these stars. So you can see this a little more clearly here. So this plot is for carbon relative to iron for a more general population of stars, specifically those with known exoplanets. The blue shaded region shows the full range from the previous slide. So the full range seen for elements in sun-like stars. So you can see it's much more limited compared to the more general population of stars shown here. Overall, oh yeah, and also I chose carbon to iron here, but all of the other elements that you could plot show a wide scatter similar to what you see in this plot. Overall, studies have focused on 3 parameters when trying to understand the composition of extrasolar planetesimals. That's the iron content, the iron to magnesium ratio, the carbon to oxygen ratio. So the iron content has been shown to correlate with the composition of many elements heavier than hydrogen and helium. So it's really useful for estimating the composition of other elements that may be more difficult to constrain compared to iron. The iron to magnesium ratio controls what type of silicate rock forms. Silicate rocks are the most dominant common type of rock found on the surface of the Earth and other planets. Pretty much any rock you pick up on your walk home will be a silicate rock. The carbon to oxygen ratio controls what type of rock forms, whether it's an oxide, like most of the material in our solar system, or whether it's carbides. As the name suggests, oxides are minerals that are made up of oxygen, and carbides are those that are made up of carbon. Overall, studies find that the carbon to oxygen ratio has the strongest influence on the type of rocks and planetesimals that form. Here are the carbon to oxygen ratios for a variety of stars with planets. The sun is at 0 on this plot. Stars that have lower C/O ratios than the sun have more oxygen and therefore more oxidizing conditions. Oxidizing conditions produce minerals and rocks that are similar to those in our solar system. While the stars that have C/O ratios that are higher than the sun have more carbon, and therefore they're less oxidizing conditions. So overall, many of these stars have C/O ratios that are similar to the sun or consistent with oxidizing conditions. Here I show an image of a green mineral called olivine, and it's pronounced olivine in Star Trek, if anybody's a Trekkie out there. It is the most common type of silicate in our solar system. This mineral is common in Earth rocks and in meteorites and in terrestrial rocks found on other planets. So when you have low carbon to oxygen ratios, you produce more silicates like this mineral. But when you have high carbon to oxygen ratios, you produce much less of these types of minerals. So in this case, meteorites could be fair analogs for planetesimals around stars with sun-like C/O ratios or stars with lower C/O ratios. Finally, here is a very quick look at white dwarf stars. These objects are very faint cores of dead stars. White dwarfs are small and faint, but they are extremely dense. So they have very strong gravitational fields, so much so that the elements heavier than helium sink rapidly below the surface of the stars, below the surface of these stars. Even so, astronomers have observed elements heavier than helium in some of these white dwarfs and have attributed this to planetary material falling onto these stars. So you have a disk of debris like asteroids that are falling onto these stars and producing signals of heavier elements. So these stars are referred to as polluted white dwarfs. Studies indicate that the material accreting onto polluted white dwarfs, this material is similar in composition to terrestrial rocks and similar in mass to asteroids. And this is what's shown on this plot here. So this plot is showing the composition of material being accreted or falling onto a white dwarf. This is for 10 white dwarfs. When compared to the bulk composition of the Earth and the bulk composition of cometary material, you can see that overall the material is more similar to Earth rocks or terrestrial rocks. So again, this is more support for meteorites as possible analogs to planetesimals around other stars. So to answer the question I set out to address and share with you today, meteorites are indeed useful analogs to planetesimals around other stars. This is particularly the case for sun-like stars and stars with C/O ratios consistent with oxygen-rich environments. This is based on the composition of the stars and on the formation of terrestrial-like rocks. So overall, meteorites can be used to study extrasolar planetesimals and to study the planets in those systems, but they may not be useful in all cases, especially in cases where there's very little oxygen. Nonetheless, using meteorites to put constraints on the composition of exoplanets and their atmospheres is a fair starting point, not only because they are the only samples available for direct measurements, but also because studies of the compositions of other stars support that chondritic or meteoritic and terrestrial-like material are fairly common around other stars. So I just want to say thank you to all the organizers and our sponsors. And I want to send a shout out to my wonderful family watching downstairs in the living room.
Great job, Myriam.
Thank you. So I stopped sharing.
Yes. So to begin, I want to ask you the same question I asked Maggie. How did you get into this? Like, why, and how did you know about this?
I've been doing this for too long, so I feel like the story gets longer and longer every time I tell it. But I think the place to start is that I did my undergrad at University of Chicago, and I was working with a researcher there who studied meteorites. So I was in the Earth Sciences department. It's officially the Geophysical Sciences department. And this professor studied Earth rocks and meteorites. And I learned a lot from just that experience. And I really got hooked. It was so amazing to see that you could use all the things I learned in geology to study these rocks from space. And then using tools like isotopes and chemical analysis and laboratory analysis to better understand what the meteorites are trying to tell us was so fascinating to me, and I've just been hooked ever since. And I'm glad that I, have a position that pays me to do this kind of stuff.
It's amazing. Yes, that's incredible. So we've got lots of questions. And first up, this is my own question. So in regards to actually your last slide where you were showing again that plot of elements of the sun versus the chondrite rocks.
Okay.
At one point in your talk, you said the reason why carbon was discrepant between the two is because carbon doesn't want to form into rocks, which really took me by surprise because aren't most rocks carbon on Earth? Am I wrong about that? I was just confused.
Yeah. So most rocks on Earth are silicates. So you have, so they're made up of silicon and oxygen. So the most common elements that make up the Earth are like oxygen, iron, nickel, silicates, aluminum, sodium, potassium. Carbon is, a small fraction of what makes up the bulk composition of the Earth.
Oh, okay. All right, cool. And then, so, are there, you talked about trying to find, sun analogs in different systems, right? But then how do different environmental conditions affect the abundances of these planetesimals you're seeing? And is there any way your work could address like very exotic solar systems from our own, relative to our own?
That's a good question. I think as long as the carbon to oxygen ratio lets you produce silicate rocks or oxides, the meteorites could be a good analog. The abundances, especially for our case, we're interested in the atmospheres of those exoplanets, right? Mm-hmm. The atmospheres are not affected so much by exactly how much iron, magnesium, aluminum you have. The atmospheres are affected by the more volatile, the more the elements like carbon and oxygen that don't want to really form rocks. So I think we could use meteorites for more exotic systems, but for systems that have oxidizing conditions. So when you get to systems that produce that have so much carbon that they produce carbon-rich planets and those kind of things, I think the meteorites then become not really analogous to what you would expect to form in those planetary systems. So I think it's, the meteorites don't help us with everything, but I think they help us with a good fraction of the extrasolar planets and more than what we would otherwise have, So, yeah.
Mm-hmm. Yeah, great. And then, so we have a question. Does the chemical composition, like the magnesium to iron ratio, does that affect the core size of these planetesimals? Like, does the composition affect, you might say, the global properties of these planetesimals?
Yeah, I think so. So if you don't have a lot of iron, then you might not make very large cores. Mm-hmm. But the planetesimals have a range of types. So you have some that don't even have cores, and so if you have, and then for silicates, if you have, depends on your iron to magnesium ratio or your iron to silicon ratio, you might have olivine versus pyroxene versus some other type of silicate. And these are just the different types of minerals that would form. Even if that proportion is different from what you get in meteorites, meteorites would still be a fair comparison, because
Mm-hmm.
if you realize from the composition of the star that, okay, actually this has half the iron than what we have in our meteorites, we can, first of all, some of our meteorites come in a range of compositions, so we can maybe look for the meteorite that's more suitable, or we can adjust our overall composition in our experiments to better match what what might be in other extrasolar system.
That's amazing. Yeah. All right. And then final question. How do you get these meteorites? Are you on like eBay or something? Are you like trying to outbid like collectors or something?
Sources.
Or yeah, or museums or something? Tell us more.
So first of all, you can request them from museums. The Smithsonian is the most common place to request meteorites from.
Mm-hmm.
You have to put in a small proposal, and say exactly what you're going to do with it, and then you have to give the meteorite back if you don't destroy it. So that's like the basic way to get them. But there are also dealers who sell meteorites, and we have trusted dealers in our community that that we trust, and we know we can get the real deal from them. So that's one of the ways. But you could go on eBay. Specifically, there are ordinary chondrites. Ordinary chondrites, they're called ordinary, but they're fantastic.
Mm-hmm.
These are just the most common types of meteorites. And because they're so common, they tend to be cheaper and easier to get a hold of. Actually, the one I have here is can't see it because it's shiny.
Space.
But it's ordinary chondrite, okay?
Mm.
And it didn't cost me very much. And so that's why ordinary chondrites could be easier to get a hold of. But you have to know what you're looking for so you don't waste your money.
Have you ever seen, I feel like maybe you haven't, have you ever seen the movie Joe Dirt?
No.
You don't have to watch it, but there's a plot.
But I've never had.
There's a plot line with a meteorite that turns out to not be a meteorite, and that. But you know what you're looking for. You wouldn't be bamboozled by that. Such a fakery, probably.
Yeah, I get a lot of requests. One of the main things to look for is metal. Look for metal in your meteorite. If you have a metal detector, meteorites have metal, and Earth rocks don't. Generally, unless they're synthetic.
Oh wow, yeah, cool.
A lot of meteorites do, yeah.
That's great. Well, I want to thank you for this wonderful talk, Dr. Tellus. But before you turn off your video, I just want to invite everybody on the Zoom call to turn on their videos and say hi to the audience, because I want to thank everybody again, and thank you, Maggie. Thank you, Ashley. Joe Burchert was our producer for this event, and he worked very hard making sure we understood how to make this all work and put this together. So I just want to thank you all for making this a wonderful event. And remember that Santa Cruz Mountain Brewing the beer garden is open right now. Ashley, is that right?
Well, not right this exact moment, but yeah.
And I'm so excited to hear more about your research, Maggie and Dr. Tellus. I think it's incredible. So again, just thank you, everybody. This was great. So I guess there's no mingling after this event over frosty beers. So, but maybe someday soon.
Hopefully.
So I guess we log out and we're done. All right. Bye, everybody.
Bye.
Bye.